Alright, let's do another least common denominator problem for two random primes. Hopefully this example will not be as simple as the one that I tried before this one. Alright, so then this is 1009 equals some factor times 349 plus some number. I don't think 349 goes into 1000 three times, because that would put me in like 1050 or something. So 349 times 2 is 698. And then 1009 minus 698 is 311. Yeah, so this is 311. Right? Let's verify that. 68 plus 15. Yeah, I think that works out. Okay, so then 349 is equal to 1 times 311 plus, I can almost read this, right, 49. And then 311 is how many times 38? Now we're going to get to 1 eventually, of course, as we already know these are two primes. Sort of like a weird setup, but I think it's going to be fine. This is like 40, so I'm going to go with 7. 210, 266. Okay, 266, 34, 45. Huh, okay, never mind, because then I can go with 8. 38 times 8 is 64, 240, 304. Okay, that's fine. And then 38 is equal to 5 plus 3. 7 is equal to, okay, so that's our final equation. Then if we start going backwards, this is 7 minus 2 times 3, which checks. Then the 3 becomes 38 minus 5 times 7. We can erase it. Okay? And then it equals, how many times 7? 11, right? 11 times 7, and I'm going to put in this equation in there already for 7, minus 2 times 38. And then I'm going to check. I already put in this equation, so I can erase it. Then that happens to be 88 and 2, which is 90. So 11 times 311 minus 5 minus 88 minus 90 times 38, and I'm going to check this number, is 3421, and this one is times 100 minus 380, which is not, which is, yeah, okay, that's fine, 20, and then 4, yeah, okay, good, there we go. So we are fine up to now doing this problem. Then now, oh, I erased the equation that I wanted. So it was 88 to 90, right? I just calculated this. I should have erased this one. Equals to 1. And then now I'm going to put this in here. But I'm going to rewrite it up here. Whatever this is, which is 349 minus 311. Okay, and that tells me this is 90. This is 101 times 311 minus 90, 349. And then this gets substituted here. So this is 101, 1009 minus 349 minus 90 times 349. Alright, so we're down to the finish line, folks. And this says I only have 101 times 1009. And then this is minus 202 minus 90. So it's minus 292 times 349. Nice. This is a nice and juicy problem. Now let's check when we multiply these two numbers that we do get. Oh, my zeros are terrible. Okay, so that's my number on the left, and this one's a beast. And of course, I'm sorry that my setup is 292, right? This is a 2, not a 7. Okay, so then this is 1, and then 9 is 81, 3600, and then 27, and then this is just 698, right? 2 times 698. Alright, so I'm getting an 8, that's a good sign. Getting a 0, that's a good sign. Then this is 29, then 2, 11, 21, 2, 10. Alright, there you have it. So, it does check all the way to the end. And what I have is, this is my linear Diophantine equation with these two primes. So now if I want to write a linear Diophantine equation with these two numbers, I would get something like this. I would do 1009x plus 349y is equal to 1. And I would know that my x0 is equal to 101. I need a better, I need to do better with my setup. Sorry, folks. And my y0 is minus 292. That means that my equations are x is equal to 101 plus 349, and remember that d is equal to 1 in here because a and b are relatively prime, and then my y equation is minus 292 minus my a. Okay, so that's what we have for the linear Diophantine equation if somebody asks us in an exam to give it.